Look at a modern aircraft wing in flight. It is a perfectly contoured surface designed to split the air with mathematical precision. But as an aircraft climbs into dense clouds, that precision is under threat. Structural icing is a hazard of aerodynamic deformation. The accumulation of ice effectively redesigns the wing's profile in real time, often long before the added weight becomes a factor. This animated diagram illustrates what happens when ice or frost begins to accumulate. Even a layer with the thickness and roughness of medium grit sandpaper destroys the wing's efficiency. The smooth, laminar airflow immediately separates into turbulent eddies the moment it hits that rough leading edge. Because the wing can no longer efficiently turn the air downward, the aircraft immediately loses lift. That accumulation can reduce total lift by as much as 30%. At the exact same time, the turbulence behind the ice creates a massive area of low pressure, pulling the aircraft backward. This parasitic drag can spike by up to 40%. For ice to actually form on the structure, two atmospheric conditions have to be met. First, the aircraft must be flying through visible moisture, like clouds or rain. Second, the temperature of the aircraft surface must be at or below 0 degrees Celsius. While a severe, thick accumulation of ice will eventually add mass and shift the airplane's center of gravity, the immediate, lethal threat is that disrupted airflow. If the wings are contaminated with frost or ice before the takeoff roll even begins, the disturbed air can completely prevent the aircraft from generating the lift required to leave the ground. Structural icing represents the thermodynamic destruction of the lifting shape that keeps an aircraft in the sky. To understand how this destruction happens, we have to look at the fluid dynamics of the clouds themselves. The atmosphere is full of supercooled drops, liquid water that remains in an unstable fluid state well below its normal freezing point. Aircraft regularly encounter high concentrations of supercooled liquid water at temperatures down to -20 degrees Celsius or even colder. When an aircraft impacts these drops, the type of ice that forms depends entirely on the size of the water droplet. If the drops are tiny, the result is rime ice. Because the droplets are so small, there is almost no thermal mass. The liquid water freezes almost instantaneously the millisecond it strikes the sub-zero airframe. This instant freezing traps air between the ice particles, building a rough, opaque, crystalline deposit directly on the leading edge of the wing. But if the aircraft encounters large supercooled drops, it creates clear ice, the most dangerous morphological form of structural icing. This diagram tracks a large supercooled droplet striking a sub-zero surface. The initial freeze releases a burst of latent heat, slowing the process. The unfrozen liquid is blasted backward by the slipstream, flowing along the wing before freezing into a continuous sheet of clear ice. The rate of freezing dictates the hazard. Droplet size and latent heat decide whether an aircraft accumulates a brittle ridge of rime or a tenacious, camber-destroying sheet of clear ice. So far, we've focused on freezing ambient air masses, but the aircraft itself can generate its own localized thermodynamic traps, creating ice where you'd least expect it. Aerodynamic cooling invalidates the assumption that the surrounding air must be freezing to accumulate ice. As airflow accelerates over the wing, air pressure drops. This expansion rapidly cools the airplane's skin, meaning structural ice can form even when outside ambient air is as warm as +5 degrees Celsius. And the temperature drop over the wing is mild compared to what happens inside a piston engine's induction system. Inside a carburetor, air accelerating through a venturi and vaporizing liquid fuel drastically drops the internal temperature. This extreme cooling freezes moisture in the air, building a block of ice that chokes the engine, especially when a partially closed butterfly valve maximizes the restriction. There's one more thermodynamic trap to consider, and it happens on the ground. It's known as cold soaking. When an aircraft descends from a high-altitude flight or is refueled with extremely cold aviation fuel, the internal wing acts like a freezer. If precipitation falls on this cold-soaked wing, it freezes on contact, generating clear ice on the ramp even in ambient temperatures up to 15 degrees. Severe icing environments exist well above ambient freezing temperatures. They are driven entirely by localized thermodynamic shifts and pressure dynamics across the aircraft's systems. To avoid these conditions in flight, pilots have to understand macrometeorology. They need to know exactly where the highest density of supercooled liquid water is hiding. In a standard atmosphere, the temperature drops by about 2 degrees Celsius for every 1,000 feet of altitude gained. This lapse rate provides a rough mathematical baseline to estimate the freezing level. However, the standard lapse rate is just a statistical average. Relying on it for tactical decisions in actual icing conditions is dangerous. Pilots must use pilot reports, or PIREPs, and live meteorological data to find the real freezing boundary. Once inside the cloud layer, the shape of the cloud dictates the hazard. In heavy, flat, stratiform clouds, the most severe, continuous icing is almost always found right near the cloud tops. This is where adiabatic lifting has pushed the water the highest, resulting in the maximum density of liquid water droplets. Cumuliform clouds are entirely different. Violent vertical updrafts carry massive, unstable water droplets to extreme altitudes, presenting severe structural icing risk throughout the column. This meteorological cross-section maps the most dangerous macrostructure, a warm front overriding a sub-zero layer. Raindrops from the warm layer fall through the boundary and instantly supercool. Flying beneath this inversion places the aircraft in a freezing rain environment, causing extreme clear ice accumulation. Pilots can read the atmosphere vertically based on what hits the windshield. If ice pellets are striking the aircraft, it means freezing rain is falling from warmer air above. Conversely, wet snow indicates sub-zero temperatures above and warmer air at the current flight level. Predicting severe clear ice demands a three-dimensional model of the atmosphere. A safe flight path depends on the temperature gradient across the entire vertical column, rather than conditions at a single flight level. The operational reality of instrument flying is unforgiving. Ice of any type on the airframe commands immediate attention and decisive intervention. An aircraft accumulating ice is actively losing its ability to fly. Even aircraft equipped with sophisticated pneumatic boots or heated leading edges have limits. These anti-icing and de-icing systems are designed to buy the pilot time to safely exit the conditions. They do not grant immunity for continuous operation in a severe icing environment. When accumulation begins, the pilot must execute an escape vector based on the atmospheric models we just mapped. If the aircraft has the performance, one option is to climb into colder air. Once the temperature drops below -40 degrees Celsius, the cloud is fully glaciated. The water is already frozen into harmless ice crystals that bounce off the airframe. The alternative vectors are to descend into warmer air, assuming there is sufficient clearance above the terrain, or to execute a decisive 180-degree turn to exit the weather system entirely. If an iced aircraft does make it to the approach phase, the pilot faces a highly specific and lethal hazard: the tailplane stall. This typically occurs when the pilot deploys the flaps for landing. This aircraft profile shows the dynamic balance of flight. The main wing generates upward lift, but to balance the heavy engine at the front, the horizontal stabilizer at the tail is an inverted airfoil. It generates a downward aerodynamic force vector. Because the tail's leading edge is thinner, it often collects ice faster than the main wing. If that ice disrupts the airflow enough, the tail loses its downward lift and stalls. Without that downward pressure, the heavy nose of the aircraft pitches down violently. Recovering from a tail stall requires counterintuitive inputs. Unlike a standard wing stall where you push the nose down, a tail stall requires the pilot to immediately pull back to increase pitch, reduce engine power, and retract the flaps to reattach airflow to the horizontal stabilizer. An iced aircraft operates on compromised aerodynamics. Hardware and pilot skill can mitigate the danger, but a deep understanding of the thermodynamic physics governing the atmosphere remains the ultimate defense against catastrophic failure.